Hello, everyone. This is round two of this video. Unfortunately, I recorded the entire thing before, and the screen recording on my iPad turned off for some reason. I must have accidentally clicked the button, which is incredibly frustrating. But hey, sometimes you got to roll with the punches and you make it work. Um, so obviously, I'm not in school today. The reason for that being that one of my daughters has the flu again, another one. My wife was in the hospital earlier today with the flu. Luckily, she is okay and she's home. Um, Somehow, knock on wood, I am still okay, and hopefully it stays that way. But in the interest of being very motivated and supportive, I wanted to make sure I had a video for you so that way we could keep moving forward and preparing for the AP exam so that way we're ready come May. So today what we're going to talk about is something that is going to be, I think, fairly straightforward for you, at least the initial part here, um, which is a two proportion z-test. So very similar to one proportion z-intervals and two proportion z-intervals. A one proportion z-test and a two proportion z-test are also very similar, right? We're going to end up using it when we have two independent populations, and we're testing to see if there's some sort of difference. So our acronym stays the same. It is Harry and the New Cat, How About Them, Nebraska Cornhuskers, Hat, North Carolina, whatever you want to call it, however you remember it, makes no difference to me. The difference now is that for our null hypothesis, it's still always written as an equal statement. However, it's now going to be that proportion from population one equals proportion from population two. And again, very much like confidence intervals, use subscripts that make sense. It saves you from having to redefine them later on in the problem. Now, the other thing that you may see here is you may see it written as a subtraction statement, as you see down here. I've seen both on the AP exam, I've seen both on the multiple choice, I've seen both on the FRQs. So I think we can handle that those are the same thing, but just know that they do mean exactly the same thing, and both are acceptable when you have to do this on the FRQ section. There is not one that is better than the other. It's just a matter of who is writing the question. That's what you're going to end up seeing. When we get to our assumptions now, again, still both samples have to be random, but we do have that one additional piece here when it comes to checking for the central limit theorem. When we had a one proportion z-test, we used the null hypothesis proportion to check for the CLT. When we have a two proportion, we don't know what that proportion is if they're equal. And so, in order to get the best estimate of what that's going to be, we create this thing called the pooled proportion, which you see over here, this p hat sub c. That's the terminology that I use here, right? But this guy over here is what we use as our best estimate, and all it is the pooled proportion. Essentially, we take our total successes, that's our numerator, and our total sample size, that's our denominator. And that is going to give us, in this particular case, our best estimate of what that proportion is if they were to be equal, which is why I have here, this is under the assumption that P1 is equal to P2. The other nice part is this is on your formula sheet, so you don't have to memorize it. You just have to know where to find it. And so notice here for our sample size calculations, we're using this p hat sub c for every single one. And so again, unfortunately, even though the problems may give you numbers, you no longer can just use the numbers like you could in confidence intervals. You have to use this combined proportion. So is it one slight additional monkey wrench? Yes, it is. Is it going to be that bad? No, it's not. I haven't seen too many two proportion z tests on the FRQs that haven't had the assume all conditions for inference have been met sentence not there. But again, preparing us kind of for worst case scenario, If you have to, here's how to do it. And it's not really that bad. It's just a little bit annoying that we may have a couple of extra steps. When we get to the test portion of this, it is just a two proportion z-test. Here is your formula. Now, again, notice here, right, that we're using the combined proportion, and this whole thing here is on your formula sheet, right? That was actually something that you saw or you may recognize from a multiple choice question, and you're like, what is that thing? This is just because both numerators would be this exact thing right here. And so because of that, we just factor it out. Now, technically in this numerator here, there's a -0 on top there. That comes from the null hypothesis. I don't write it. So again, you may see it in some multiple choice answers, but we're going to do plenty of in-class practice on that. So I think that will clear up anything you may have. And again, this formula is only for the multiple choice. If it's a free response question, you can 100% just write two proportion z-test and move on with your life, which is what I highly encourage you to do. For our numbers section, I put this here. You don't have to list it here, but that combined proportion has to show up somewhere, whether it's in your assumptions or it's down here. It's got to be there somewhere in the problem. So we need our z-value or our test statistic, our p-value, and your significance level. And your conclusion is going to be the same as before. Compare your p-value to your significance level, and then decide, do I reject? Do I not reject? And then, do we have evidence of our alternative? Do we not have evidence of our alternative? And so, I have an example here to run you through that apparently has not shown up. So we're going to roll with it because I'm not going to record this video three separate times. Maybe if I minimize this, it will look a little bit better. Because this looked a lot better on my iPad before when I had this. All right, we're going to pretend this is fine. You have two elementary schools. It's hard to read. I will upload this from my iPad so you can actually read what's going on here. Um, but essentially, the idea was we're trying to test for a difference between the students who have and who have not eaten breakfast um, before coming to school. And so what you can see, right? Actually, here's what I can do. Let's make life a little bit easier here. And I can get rid of this and I can move it up here. All right. So this is a little bit easier now for us to actually read. Much better. I'm not sure what I was highlighting up here, so we're just going to get rid of that for the moment. And then I'll re-highlight it again. But again, so if we read this problem, we've got a simple random sample of 80 students here. Right, we have 80 from school 1, we have 150 from school 2. And now in this particular one, the other important thing was difference. Right? So that's how I knew that in this particular case, my alternative, if you take a look at that, is just that it's not equal to. Right? We were just testing for a difference in proportions. So didn't give me a specific direction. That's how I knew we were here with not equal to. So I define my hypotheses. In my assumptions now, I have an SRS from both schools. But notice over here, I have my combined proportion. And I use my combined proportion right here in order to determine my sample sizes. Right now, again, I would show this calculation fully out and actually get a number. I didn't have a calculator in front of me. Therefore, take my word for it. That combined proportion is roughly 0.2. It's pretty close to it. And so 80 times 0.2, we're just fine. I have a two proportion z-test. This is the printout from your calculator. If you go to two proportion z-test, again, select not equal to. What's important is this highlight here in pink. This is your p-value. This p hat down here is your combined proportion. Obviously, p hat 1 and p hat 2, those are from your first sample and from your second sample. But that standard p hat without a subscript is your combined proportion. So very easy way to check and make sure you did something correctly. But this also, this p here without a hat and without a subscript is your p value. So this guy right here is obviously going to be important to your conclusion, which is why you see here when I say p equals 0.24, we do not reject our null hypothesis. If I was going to continue this, we do not have sufficient evidence to show that there is a difference in proportion between these two schools for the number of students who do not eat breakfast. And so again, on your calculator, it's very simple and straightforward. You just plug in x1, n1, x2, n2, and make sure you are selecting the appropriate alternative hypothesis. That's the important thing. Now, the last thing I wanted to talk about, and all of this stuff should not be here, it should be further down. So let me see if I can move that quickly for us here, because that would be cool. Um, is something called the power of the test. And so the power of the test is the probability of correctly rejecting a false null hypothesis. So all of this stuff should be underneath this, but this is what happens, guys, when you go from an iPad to your computer with this sort of thing. So we'll make this just a little bit smaller and move it over. So a couple of important notation things for you. So again, power of the test is the probability of correctly rejecting a false null hypothesis, or in plain English, it is the probability of a true positive. The probability that I actually have the disease and the test says I have the disease. So some other important notation things for you. The probability of a type 1 error is just alpha. That's it. It's possible that I'm in the top 5% and my null hypothesis is true. The probability of a type 2 error we denote with the letter, or the Greek letter, beta. The thing is, beta is impossible to calculate unless I knew the population numbers, which I don't know. And so the power of the test is 1 minus beta. And so to give you a little bit of a visual here as to what this would look like, I have this graph over here. Now, it may be hard to read, but in here, right, that's an alpha right there. If I go back to my laser pointer, right, like this is an alpha right here. And this little spot right here is my beta. This is the probability that I don't reject the null hypothesis, but in fact it's false because here, this green distribution is my null hypothesis. All of this shading over here, right, all of this in here, this is all the power of the test. But again, it's impossible to calculate without knowing the true population number. And so the thing that's important about the power of the test is that it's just knowing that there's always going to be some sort of push and pull. If you make your significance level smaller, right, you make it harder to reject the null hypothesis, you decrease the power of the test, and vice versa. So there's always going to be this push and pull between type 1, type 2 error, and the power of the test. Because as I make my significance level lower and I decrease the probability of a type 1 error, I increase the probability of a type 2 error. So again, that's why when people ask about, what significance level should I pick? It depends on the context and it depends on which error type is going to be worse. So I have some example problems for you. All right, so if we take a look at this first one here, again, these are multiple choice questions, and that's really where you'll see this for the most part. And this comes straight from AP Classroom. I just took a screenshot. And so we have this person who's running for governor, and he believes that more than 30% of voters are already supporting him. He's going to take a big survey. And so what's important here is they're giving you the population number, right? They're saying, suppose that 35% of all voters actually support him. There's my population number. So, in which of the following situations would the power be the highest? Well, that would be in which of the following situations am I going to be most likely to reject the null hypothesis because I should, right? If my initial assumption is 30, but the true value is 35, I should reject the null hypothesis here. And so, in order to make it the easiest to reject, it's the highest sample size and the highest significance level, which is why here the answer is E, the largest sample size of 1,000 people and the biggest significance level of 0.05. Right. A actually has the lowest power of the test. I got to be in the top 1% with the smallest sample. And the reason why we want the big sample is, again, think like law of large numbers. Bigger sample, closer to 35%. Now, the other type of question you may see is something like this, where we're testing for the mean being less than 10, and we're assuming that the alternative is true. For which of these values would the power be the greatest? And notice it says fixed sample size and fixed significance level. So all I'm looking for is a mean that's the furthest away in the direction of the alternative. So in this particular case, what is the smallest number less than 10? And so that happens to be 8. And that's why this is my answer, right? It is the smallest number less than 10, highest power of the test. So I understand with power of the test, we may be a little bit on the rickety bridge in the rainforest right now. Hopefully a two proportion z-test is fairly straightforward for you. But I should be back Wednesday, uh, assuming everybody is okay and I also don't get sick. And so I'll be able to answer any and all questions you have. For the time being, I left you guys a practice worksheet along with an answer key. And so I will see you guys on Wednesday. Bye.